Welcome to the BALISP meetup in late April 2023. Today we have the pleasure of hearing two interesting speakers. The first is Reynolds Freeman, who's going to talk about his Wraith Scheme. He's coming in via Google Meet. After that, and he's also going to tell us about his work porting it to the Apple M1 architecture. And then after that, Stephen Watson is going to talk about the Nanopass Framework for building compilers, which is used in Scheme. So yeah, take it away, Jay.
Hi, everybody. Double check. Can you all hear me?
I hear you. We hear you.
Okay, excellent. I'm Jay Freeman. I'm talking about a scheme application called Wraith Scheme. And I did check all the attendees who'd registered for this meeting as of a week or so ago. None of you were even present members of the group when I talked about Wraith Scheme last, so I thought I'd start a little bit by talking about its history and how it came about. In any case, this isn't a talk. I can't say it's a sideshow. You get to see alive what kind of fool would build an entire R5 scheme from a clean sheet of paper. This is my cue to take a bow. Actually, you can't see me. You can just see my cat icon. That's probably just as well. Who am I? The PhD says physics. I worked in an astronomy group. I call myself a used astrophysicist for cheap. I've been a career programmer. Didn't do any work at all in astronomy after I got the degree. I have moderate experience in Lisp and artificial intelligence. I spent a couple of years sitting in front of a Symbolics 3600 way back in the days. I'm pretty informal, so feel free to scream and throw things and ask lots of embarrassing questions anytime you like. I expect this talk will take less than an hour, and there should be plenty of time for questions at the end of it. But if there's something isn't clear, or you can't hear me, or you think I misspoke, holler. Wraith Scheme is an R5 scheme with a lot of enhancements. It runs on the Macintosh. It's run on a couple of other Apple platforms, and lately I ported it to the Raspberry Pi. Does parallel processing on a Macintosh, and I'll tell a little bit more about what that is in a moment. There's plenty of documentation and a download. As I say, if you go to my website, which is www, come back. If you go to my website, which is shown there, www.jreynoldsfreeman.com, and there's a push button at the top that says software, and you go to software, and there's something that says Wraith Scheme 64 bits. You can download the program and any of the documentation you like. It is open source. You can get a source download, but it requires Xcode in the tool chain. I don't have a GitHub repository for it. It'd actually be too large for the what GitHub allows for free, but there is source available. History started in 1987. I was working in an AI lab. I was quite interested in Lisp systems and how they worked. I wanted one to play with, so I built one of my own. It started out as something called Pixie Scheme, which would run on the original Macintosh in Mac OS 4. That's not a version of OS X. That's the original Mac OS 4 for the original Macintosh, and it was written in C. I released the version at that time. Anyone could just send me a floppy disk, and I would send them a copy. In 2006, I ported it to C++ and then to the Intel and PowerPC Macs. And it was a big enough port that I decided to change the name of the system to Wraith Scheme, uses the Mac graphical user interface, Xcode, and Objective-C. And I added a couple of terminal shell versions for the same program running with a simpler user interface for reasons which will become clear in a bit. In 2007, I added parallel processing. In 2010, I did a port to the iPad as Pixie Scheme 3, which is no longer available, but it was there. Last year, I ported it to Apple Silicon, and just recently, I ported it to Raspberry Pi as Weasel Scheme. And Wraith, Pixie, and Weasel were all cats, and I like cats. And there's sort of a feline metaphor that goes throughout all of my stuff. There's a picture of Wraith Scheme. But rather than show you the picture, I'll just open it up and show you what happens when I start running it. Oops. Let's quit it and start it again. Okay, so here you see it opening up, and you see a couple of windows have opened up. And when it starts running, it starts reading a demonstration program. It would be appropriate if somebody didn't know anything about Scheme. And while the demo runs, I'll show you a few things. There's a panel over here, this one that's opening and closing, that has some buttons to push if you like to run a program by pushing buttons. Down in here at the bottom, there's kind of an instrument panel that has some data about what the program is doing. There are a couple of other pop-out drawers. This one has some buttons and switches and sliders. And there's even something I call the attic, which contains a lot of links to other kinds of things that aren't really part of the program, but which might be useful. When you're done looking at the demo program, you can shut it down. There are plenty of menu commands, reset to top level loop, and presently it's stopped. And now you see it's just a regular Scheme implementation. If I type +22 and hit a carriage return and evaluate, there's 4. And there are these other windows. At the moment, it's configured to run with 4 completely separate Apple processes. These are separate Unix processes. They're all using a shared Scheme main memory, so that if I define something in one of these windows, the other windows can get at it. And if you look down here at the bottom, in the Macintosh toolbar, the Macintosh dock rather, you'll see there actually are a lot of little windows in slightly different colors to correspond to the different Macintosh programs that are running. So there's really 4 different instances of a Macintosh program which are communicating with one another. In any case, the architecture of Wraith Scheme is a little weird. There's a book which was very influential in how I wrote it. It's called Functional Programming Application and Implementation. It's by Peter Henderson. Henderson was interested in talking about functional programming, but his descriptive means was very interesting. He developed what I would have to describe as an applicative subset of Scheme, where no operations had any bangs, no rebinding of variables. And he described it running on a virtual Scheme machine, which he described in this book at the register transfer level with an assembly language all of its own. And this was an interesting and concise and complete way to describe an implementation, except there was no real machine to run it on. Henderson used, though he did not invent, something called an SECD machine. The way his virtual Scheme machine worked, if there were 4 registers that pointed into main memory. One was a stack. That's not the kind of stack you use for function calls. It's the one you all learned about in beginning computer science for doing arithmetic. So for example, if you wanted to add, you push 2 things onto the stack, call an add routine, and the answer ends up on top. Then there's the environment, and there are many ways to represent environments in Schemes and Lisp, but he had a register that pointed to the particular instance of environment that was in use at any given time. There was the continuation, which basically is a list of all the instructions that are left to execute in the current basic block. And then there's the dump, which is like a call stack. When you're starting a new function application, you wrap up the existing stack execution and continuation as a triple and push it onto the dump. When you return from the call you just made, you pop the dump. I added some more registers and changed the implementation of a few things and added means to rebind variables, and I had a small Scheme, but it was still running only on a virtual machine. What I did, I remember the last meeting we had a couple of weeks ago, some of the folks from Xerox PARC were there who had developed some of the Xerox PARC Lisp machines in the 1970s and 1980s. I hope some of them are still here today because I wanted to say thank you, because I used some of the work that they had published on how the Dorado and the Dolphin Xerox machines were published, or how those machines worked, in figuring out how to make my own architecture work. I implemented Henderson's SECD machine by using C preprocessor macros for assembly language instructions. The macros expand into C, which in essence becomes the microassembly language for the virtual machine. This sounds sort of weird, but as they say at the bottom, it's all just 1s and 0s, and that's fine. So the microassembly language also has another feature. This was a wonderful thing that Xerox PARC did. And when you're running the microassembler could call out to routines of arbitrary complexity, even routines that are written in Scheme itself. So the Scheme primitive operations are implemented as a series of, quote, assembly language instructions that are compiled into C, actually C++. This layering simplifies the architecture and facilitates changing the physical processor used by the implementation. Let's see a little bit more about how that works. In Scheme, you might ask the interpreter to evaluate +2, 2. The evaluator calls up some code that implements plus. What does that code look like? Here's an example. And this should look very much like an assembly language, only it's not. These are all macros for the C preprocessor. There's a procedure that's called add, and this is how you add something that has an arbitrary number of arguments. You first to check and see if there are any more left, and if continue is returned, and here is where you are pushing things on the stack and decrementing the number of arguments you have left to do, and here there's this operation called add. So this ought to look sort of like assembly language at some level. Here's how it translates into C. And here's what they look like side by side. So you can see this statement is simply the start of a function. Here is something that checks B as a register. It checks to see whether the accumulator, that's R, is 0. It stores the result in B. Here it's doing some go-tos. Here it's doing some stuff manipulating the stack. Here it's a swap operation. But look at add. Add expands into a call to a function which is actually quite complicated. So here in the first, here is the same function with some comments showing you what's going on. And here is the first fraction of a page of the big routine called add, which has to do a whole lot of stuff. It has to deal with the possibility that the things that are adding are any combination of fixed num, flow num, complex, rational, cope with infinities and nands, and it has to perform various kinds of locking in the heap to make sure that multiple scheme processors do not interfere with one another by trying to do simultaneous reads and writes. So the C and C++ that the preprocessor macros expand into for the C code for the big add function have changed often as I've added features to Wraith Scheme. But the virtual machine assembly language for add code has not changed in more than 30 years. So here, once again, here are the architecture layers. The first architecture layer is Scheme source code, like +2, 2, and 2. Then there are Scheme primitives, like plus or list or cons. Then there's this assembler stuff, the stuff that looks like assembler, which is implemented in C++ routines. And finally, there's compiled machine language. And this layering separates one big complicated mess into a lot of smaller and simpler messes. And that, as I think you can understand, is a big win. So re-implementing Wraith Scheme for a different processor or operating system is merely a matter of changing the tool chain, not of changing code. So in answer, getting to one of the subjects in my talk, most of the business of implementing Wraith Scheme on a different processor, such as going from Intel Silicon to Apple Silicon, was trivial. You just change the compiler, verify some flags are right, and off you go. There's a part that isn't, and I'll get to it. That also means that as compilers get better, Wraith Scheme runs faster. It's not as if I myself were maintaining my own scheme to assembly language or scheme to machine language compiler. I'm relying on existing compilers to generate code. Those are also big wins. There's some other pieces to the architecture. There's a storage allocator that manages main memory. There are garbage collectors. I have both a stop and copy and, in Wraith Scheme at least, a generational garbage collector. The evaluator itself, the E in the REPL, is a big fuzzy loop, and it has to be just right. There is a compiler, but it doesn't generate the machine language. It compiles to threaded code. If you've ever heard of force and know how that works, think like that. What it does basically is does all the symbol evaluation it can in advance and all the unraveling of ifs and elses that it can in advance. There's an ob-list. There's only one instance of any given symbol, so symbol equality is just a matter of pointer equality. You never have to compare the name strings. And to build this system, some of the Scheme primitives are written in Scheme itself. So to build it, you compile Wraith Scheme, the C++ as a C++ program. And it contains enough primitives so that the Scheme compiler can create the written in Scheme primitives in Scheme main memory. Then you save a world. Wraith Scheme has world save facilities. I suspect most Lisps do. You arrange to load that world automatically whenever Wraith Scheme launches. So that particular world, which is embedded in the application itself, is sort of essential DNA for Wraith Scheme. Now let's talk about parallelism. I showed you Wraith Scheme running with 3 kittens. The metaphor here, incidentally, is cat-like. This main window, the one that's yellow, I call the mom cat, and she has supervisory privileges in certain circumstances, notably in garbage collection. The other ones I call kittens. And so you have the image of a rambunctious bunch of kittens and a mom cat trying to provide herd on them. There really, and this figure, there really are 4 separate instances of Macintosh Wraith Scheme application, as I showed you. There are 4 separate graphical user interfaces. If you do PSAUX, you get 4 Unix processes. Scheme main memory is common to all 4 processes. It's memory mapped with lockless coding to avoid disasters. And you do get disasters, trust me. What good is this kind of parallelism? Multiple actors. One of the things that Scheme is good for is one little program comes and does something, and then because of tail recursion, it doesn't have to return to a caller. It can just call the next thing, the next program that's supposed to do its little bit, and programs will call one another. Having parallelism of this sort allows multiple strings of actors to be operating at the same time. Sometimes it's useful to have whole different programs operating. You like to have 2 Scheme programs running and maybe share data, that's fine. It's useful for debugging, and I thought it was neat. I've spent most of my professional career dealing with parallel processing in one form or another, and it was kind of neat to build a Lisp system that had it built in. There can be up to 31 of these kittens. Here's a picture showing a rather frazzled mom cat with 31 of these kittens. And if you look down there at the bottom, there in the dock, there really are 31 little tiny icons, all in different colors, labeled with the kitten number. There's less burden to having a lot of Scheme processes running than you might think. You only need to load a given page once. The operating system knows it in there, and if more than one process requires it, it'll simply map it into their address space. There is probably some cache sharing, and the idle processes, when they are idle, don't use very many cycles. There's a major problem with parallel processing, however, and this is the one that was the headache when it came to porting, which is simultaneous memory access. Clearly, there could be confusion if 2 processes tried to write memory at the same time, and what got put into memory was part of what one process wrote and part what another did. The minimum memory element size in Wraith Scheme is 2 8-byte words, and they are accessed separately. So you really do have the risk that one process might be writing one word while another process is writing another. The first word is a tag that describes the data. The others are actual data. Processes always have to see the proper tag for the data. It would be a disaster if you wrote data that was a string and a tag that said, oh no, this is an integer. How do you do that? Locking all of memory is too slow. You could do that. That's a simple solution. But it's faster and better to lock individual memory elements. And for some reason, some historical reason, this is called lockless coding. Go figure. I think originally it was a novelty which came up when people were used to locking all of memory, and somebody figured out you didn't have to do it. They called it lockless coding. Apple used to have built-in atomic operations to do lockless coding, but and I used them in the early development of Wraith Scheme, but they deprecated them recently. So as of 2022 and now, each processor type needs assembly language routines to do the job. Those routines are substantially different on the Intel architecture and on the Apple Silicon architecture. I'll mention in passing that the port to the Raspberry Pi was extremely easy. The Raspberry Pi version, I don't have any slides of it, it runs in a terminal shell, and it's not parallel. So I didn't need any assembly language routines for locking. I didn't need any fancy graphical user interface. All I had to do was get G++ running on the Pi, plus with some compiler flags to be sure that it was implementing the right, it was running the right version of C, and it came up and ran. So that was a big dividend from using C++ as the microcode. In the case of a non-parallel system using a simple graphical user interface, the port to a totally different processor was absolutely trivial. I named that port Weasel Scheme. Now let's talk about what you do when you update the Macintosh application. The C++ and Objective-C parts of it ported trivially, The Apple compilers were all set up to compile code both for the Intel application and for the Apple Silicon application without any thought. Lockless coding took some work. Each of those tags that I mentioned has a lock bit, and any Wraith Scheme process must be able to test and set or test and clear that bit atomically. And the rule is that if one Wraith Scheme process wants to either to read or write a data element in scheme main memory, if that data element is locked, the process that wants to read or write it has to spin and wait. Presumably it's locked because some other process is using it, and the other process will unlock it presently. Wraith Scheme C++ code is written so that one process is locked to tag. No other Wraith Scheme process can read or write that memory element. And that's not something that the hardware will do for you automatically. You have to write code that guarantees that this locking is observed. So lockless coding is conceptually simple, but the truth is in the details, and the details tend to be a bit of a mess. Memory operations are very slow, by a factor of 1,000 or so, compared to instruction execution. So processors schedule memory operations efficiently, not necessarily in the same order in which the instructions which cause the memory operations took place. Disk access is even slower. There's another factor of 1,000 there. It's interesting. I suspect most of you know it. It used to be that when you were trying to optimize a program for speed, what you wanted to optimize was instruction count. Fewer instructions meant things going faster. What you want to optimize these days is locality of reference. You'd like to minimize cache misses and page faults. You're talking about a factor of 1,000,000 or between how long it takes to run an instruction and maybe how long it takes to refresh a page if you need to. You have to do a lot of instruction minimization to get back 1,000,000 clocks. So modern processors queue up memory and reads and writes. The queues are long. It's to save time. Memory operations may not execute in the same order as the instructions that generated them. These are the headaches. Each processor on a chip may have its own queue of memory operations, which are to be executed at some time. And the enqueued memory writes may be read back into the processor if you execute an instruction to read something that you just wrote. The caches may get read or flushed or overwritten during memory operations. So for one processor to do a test and set operation, you have to do the following things. You have to stop the other processors from enqueuing memory operations. Then you have to flush all the operations in all the queues. Then you do the test and set operation. Then, if the test and set operation was successful, that is, if the bit in question was not already set, then and only then are you cleared to go ahead and modify the data or read the data if that's what you wanted to do. By propagating memory operations all the way through to memory before doing the test and set, the locking operation guarantees that no pending operations will alter either the lock bit or the associated data that the locking process is changing or using. Conceptually very simple, but hard to do because of the memory hierarchy that I just mentioned. Now, so you've just changed some lock data. How do you clear the lock bit? What does that mean that you have to do? First of all, the processor that locked the data has to flush its own queue of, flush its own queue of pending memory operations. That's to ensure that the changed data has reached memory before it clears the lock bit. And once that queue has been flushed, then the processor that just altered the data can clear the lock bit. Excuse me a moment here. I'm pouring myself something to drink. And by propagating the changed data all the way through to memory before clearing the lock bit, the process ensures that the data that it has just altered will be available for all subsequent operations by other Wraith Scheme processes. That, in a nutshell, is the problem with doing parallel processing with lockless coding. Let's see a little bit how to do that. The Intel x86-64 architecture, which is what Apple's been using in its processors for more than 15 years or so, it makes lockless coding relatively easy. There are assembly language instructions for test and set, test and clear, and there's a lock prefix that does all the flushing. I haven't given you the whole routine that does the lockless coding. It has to do with figuring out addresses and going fetching what lock bit and so on. But basically, the routine the assembly language instruction that matters is the one that's shown here in red. Lock, bit, test, and set. And two-word pointer to a quad word unless it's such a location. And that's really the only instruction you need to worry about. Put those in the right place and you're home free. Now there's an interesting side about the Intel architecture I should mention. To my surprise, I found that there was a published paper in a refereed academic journal about research whose sole purpose was to find out how the x86-64 locks and flushes code. It's written down here if any of you want to copy it down. I doubt any of you do. What this means is that somebody in the academic community thought that Intel's documentation did not properly describe what the product did. And that's a little scary. It's scary for two reasons. First, they might be right. The documentation might have been incomplete. I think they are right. I've looked at Intel's documentation and it's a little fuzzy. It also makes you worry whether Intel actually knows what the processor does. I've worked with microcoded processor architectures in a couple of jobs. And I recall one company I worked for, it wasn't Intel, which we almost lost the hardware, the description of what the hardware on a chip we had built did. We had to go and fetch it back by reverse engineering, and we did, but it's scary that people can make mistakes like that. For reference, here's a picture from that paper that shows the programmer's model of the Intel architecture. Here there are different hardware threads. These would be Wraith Scheme processes. Here's this write buffer, and here's something that locks things, and here's the shared memory. And that obscures a lot of detail. There's nothing in here about page fetches, and there's nothing in here about caches. There are lots of caches up here, and there would be page fetches and whatnot in various places. And for the Apple Silicon architecture, which is basically the Acorn RISC machine 64-bit architecture, lockless coding is more complicated, but seems to be a little bit faster. The ARM64 is prepared to try to do a test and set or a test and clear, but it can't guarantee that it will have done so. It is quite possible that while your process is trying to do a test and set or a test and clear, some other process will have altered the bit you were interested in while you were looking at it. And the ARM64 architecture is prepared to try optimistically to do what you want, but to report if it failed. So in the ARM64, a test set can fail in two ways. One is the traditional way. The bit's already set. That's what happens in the Intel architecture. The other way it can fail is because another process interfered with the planned operation. In either case, you have to spin and wait until you get a test and set that succeeded without anybody else interfering. Furthermore, there are specific memory barrier instructions for the flushes. It's not like having just the lock prefix that Intel has. You have to put them in the right place. I don't suspect you want to read this, but here is most of the code for test and set that I used in the Apple Silicon version of Wraith Scheme. And the instructions that are marked in red are the ones that specifically have to do with the locking and checking to see whether there's been interference and so on and so forth. All the rest is just arranging to set up the addresses of everything correctly and be sure you're working of the right bit. So it's like 5 instructions instead of 1, and there's some root, and there are a couple of jumps, and you have to put the memory barrier operations in just the right places. And this took a lot of tests to get going. It was a new architecture for me, and I hadn't actually written any assembler in any architecture for a long time in 2022 when it came time to support Wraith Scheme and update the way they did things in the Intel architecture. So in summary, I think Wraith Scheme's idea that everything is C++, everything in the architecture is C++, makes most of porting a no-brainer. You just change the compiler. But lockless coding for parallel processing requires a different assembler, and some of it is sneaky. Different systems may, of course, require different graphical user interfaces, but those are easy to factor out and rewrite. Wraith Scheme made a pretty good job separating the graphical user interface from the underlying scheme machine, the thing that does the actual scheme. So I'd like to say thanks for inviting us. If there are questions, I'll take them. If there are not, I maybe could show you a few more things about what Wraith Scheme does. I'll let our moderator decide what to do. Arthur, over to you.
All right. I will call for questions either in the room or virtually. Anyone have any questions? Yes.
I have a question regarding using of C++. Is it some features of C++ which are like necessarily used, or is it just C mostly?
I didn't hear all of the question. You were asking about C++. Doesn't C++?
He's asking why C++ in particular are you using features of C++ that C doesn't have?
Yes.
I switched from C to C++ because it was the natural thing to do in 2006. The time I started out writing Wraith Scheme, there weren't any decent C++ compilers. The GNU compiler was sort of up and running, but it was buggy. Apple had one object-oriented compiler available. That was an Object Pascal, but I had a feeling that Pascal wasn't going to go anywhere. So I started out in C. I ported to C++ because I wanted to use object-oriented programming where possible. C++ does have some features which allow for locking, but all the C++ features that require locking require at least one extra word. And the minimum size of a Wraith Scheme object is 2 words. Adding an extra word just for the purpose of locking, just so I can use the C++ stuff, increases memory usage by several tens of percent. And what's worse, it makes cache misses more likely. So I would rather work with locking just one bit rather than use the C++ stuff that's set up for locking. Does that address the question?
Yes, sir.
Sure, I fully understand the answer, but it probably addresses the question.
Arthur will have to elaborate. I can't hear everything over the microphone.
Sorry, he's not quite sure to answer the question. Maybe you wanted to understand why he wanted to use the object-oriented features of C++?
Yes.
Yeah.
Jay, could you write that macro assembler for the Wraith schema using only standard C features without object-oriented parts of C++?
The answer is yes, and by and large, that's what I did. Most of the microassembler stuff dates from the days when I was only using straight C. The object-oriented features that I used had to do with some aspects of the program that I did not describe in detail. If you're curious, download some of the documentation, and there's an internals guide to Wraith Scheme. Let me show you just a moment. Let's see if this works. There's a lot of documentation. I'll tell my joke on myself. I like to write, and the total amount of documentation I wrote for Wraith Scheme, the word count is about halfway between Pride and Prejudice and War and Peace. There's about 300,000 words of documentation. There's a document called Wraith Scheme Internals. Oh, let's see, just a moment. I will have to move that up here, stand by. Arg.
Is it possible to make the font larger?
Just a moment. Hang on. The document is actually accessible from inside of Wraith Scheme, but I'm having trouble making it come up in the right place on my monitors. So there's this document, which I suspect you can read. It says what's inside of a cat, and it describes a lot of things about how the architecture is, and the section here on object-oriented code and what I did with it. If you're truly curious, you can download this from my website and read it. Basically, I used the object-oriented coding for some features of the system that I didn't talk about today, notably the garbage collector, the storage allocator, and some of the means whereby the different separate Wraith Scheme processes communicate with one another. However, historically speaking, Wraith Scheme was written before object-oriented coding was available, before object-oriented compilers were available. I used an object-oriented coding style. I did what we all do. I wrote a lot of things that look like the kind of stuff that the early G++ produced. Early G++ basically do a set of preprocessor macros to do object-oriented programming. You got a lot of things that were a lot of objects that contained pointers to functions that were passed an instance of the object, and so on and so forth. I hope that will do it. More questions?
Can I have another?
Yeah, go ahead.
Why Thief's revision of scheme?
Arthur, repeat, please.
Yes, why R5RS?
Why R5RS? Well, it originally started as an R3 scheme and went to R4 and R5. At the time the scheme community was progressing on beyond R5, there was a great deal of debate about what R6 was going to be. I sort of covered my eyes and went away at that point because it was clear to me that whatever R6 was going to be, it was going to be much too large for me to maintain. Our Wraith Scheme has been developed as just by me. It's taken probably, the total time it's taken is probably several person years of my career just for fun. R6 was so much bigger that I didn't think I could handle it. I personally was not pleased with some of the features of R6, but that wasn't why I didn't support it. I didn't support it simply because it was too big. After R6 came R7. R7 is small enough that I could in principle support it, but unfortunately R7 retains some of the features of R6 that I didn't like in the first place. And there are a few things, notably the notion of what a library is that would be very difficult to implement in Wraith Scheme for reasons that are, it would take a while to describe. So at the moment, Wraith Scheme is basically R5. It has a lot of features added beyond R5. I won't say a lot. It has some R7 features added, but it's probably never going to go all the way to be an R7 scheme. I'm not entirely happy with that, but I think the answer is that Wraith Scheme diverged from the official version of what Scheme is about the time that R6 split off, and it would be hard to re-merge it.
So speaking as one of the editors of R7RS Small, I know we don't have time here, but I'd love to talk to you privately about,
Certainly.
what technical reasons there were.
Certainly, we can do that, Arthur.
Yeah. And then for R7RS Large, we're trying to have as many SRFIs that have portable implementations as possible, so that it will be easy. So it might be possible for you to skip directly to large, but R7RS Large. But at the rate we're progressing, it may be many years before that's ready. But anyway, are there any other questions here or virtual?
I can show you something cute in just a minute.
Let me ask you one question, which is, now that you have Wraith Scheme, I mean, you've had it for many years now, have you built anything in it? Have you written any programs in it that are fun to talk about?
Probably the most fun program I've written about with the Wraith Scheme compiler, and that was an interesting thing in its own right. I tended to use it for mostly small things. Most of the challenge for me was developing it in the first place. I can show you, by coincidence, I'm setting up to show you something here that is possibly an example of an interesting program. I've opened a window, what I call the kitten graphics window. It's a logo style window. I'm going to cut and paste from another window, which you can't see, into Wraith Scheme. Let's see if this works. It's compiling a bunch of stuff. And let's go here, and let's change the window color. This metaphor, incidentally, instead of turtle graphics, what we have here is a kitten pushing a ball of yarn. And it's cute, of course, but I like cute. So let's see. I split this off to that side and leave this where you can see it. Let's see if it's going to work today. So there's your canonical demonstration of how to make something that's really just a bunch of circles, but at least looks pretty in turtle graphics. But that's probably one of the more interesting features I have in Wraith Scheme. I've written some stuff. Let's see. Up here in the attic, well, you can get hold of several other versions of the code. I've written some code that works with quaternions. I've written some code that calculates all the permutations, the first n numbers, without having to store a list of the permutations. And that's useful if you're dealing with permutations that have more than a few numbers, because the lists get awfully long, awfully fast. I've written some code here that is a generalization of associalists, which allows for multiple predicates and multiple things in lists. Some of this is fun. This is code that sings 199 bottles of beer on the wall. At one point, I did a version of Wraith Scheme that worked on the cloud, so to speak, or not really on the cloud. I did a version of Wraith Scheme that was able to talk between different computers, not just different instances, not just different applications running on the same computer, but I could have different Wraith Scheme processes running on different computers, and they could talk and exchange data, and that was kind of fun. That should probably do for a while. I think I probably answered that one enough.
Okay. Any other questions? Otherwise, I'll ask another. So I'm curious. You decided to do threading. Sorry, do concurrency at the process level instead of at the thread level. Did you? Were there some trade-offs that you were considering when you made that choice?
The basic trade-off was I wanted to have as many instances of the Wraith Scheme graphical user interface as there were threads. And the straightforward way to do that was to make multiple processes.
That makes sense. And then I guess one last thing is, have you ever considered opening the project up to others to contribute?
I'd welcome contributions. I have a feeling that this Wraith Scheme is very little used. I suspect you could count the number of users on the fingers of both hands, maybe even less. It was more popular a decade or so ago when the scheme was more used for education. I would welcome contributions. You can get source code. If you look at the web codes at the web page I just cited, you can download source code to your heart's content. The project as a whole is a little big for a GitHub repository. It's over half. I'd have to, let me find out just a moment. We can do this. But let's see, hang on. I've got 4 monitors here. What you see, what's going on when I'm not talking is that I'm fussing with something and lots of other monitors.
Or many monitors, many sorrows, he says.
Yes.
Well, I guess
It's the total download, the total size of everything, including the Git repositories, which I use locally, is over half a gigabyte, and that's a little large for what GitHub does. Furthermore, the other problem with making it public is that the tool chain is not something you can just download a version and build. Each version of Wraith Scheme requires a particular version of Xcode to build. So it's, you see what I mean? It's not really a good fit to the way GitHub, for example, does things. I'd welcome participation, but putting it in a Git repository isn't going to make it very available.
Yeah. Well, If there are not any more questions, I figure we should thank our speaker. Thank you very much, Jay, for this interesting talk.
So today I'm going to be going over Nanopass, and what Nanopass is a framework or domain-specific language for constructing compilers. So today I'm going to show you guys how to make 2 passes in a Nanopass compiler. Okay, but before I do that, let me show you how the compiler works. So, load the file into the REPL, and then I have a function here to compile an expression. And I compiled everything. Let's go run program. You can see that it produces the correct output, which is good. So the first thing, one of the first concepts in this domain-specific language is the ability to define a language. So I'm going to define this or not language right here. Okay. So to define a language, you need to define its terminals. And then you also need to define, some, what are these called? Like clauses. So this is a clause called a program. Okay. It takes this form. And this is a clause called an expression, which takes this form. Once you define a language, you need to parse that language. You need to get the language into the environment. So you can do that with define parser. Okay. So define parser will create the parser for you. But actually, since it's instructive, it would be good to just define the parser as a pass, as was done here. So I want to show you guys this pass. I want to show you guys this pass in the REPL. Let me try to get. I'm going to say parse. And I want you guys to look at these clauses in this match statement. Okay, so the first thing in this list, it looks for the symbol program. So if you're familiar with writing compilers like this, you've probably seen this before. So that's what I'm going to do. I'm going to write an S expression called program. Also a middle part too. And right here, it takes an exp right here in the third part. So I'm going to write an exp. 5. Let's try to parse it. So parsed it just fine, but it turned it into this sort of opaque value, and that's what Nanopass uses to match on. Okay. So now we have the program text inside of Nanopass, and we can write maybe a more substantial pass. So it'd be great to extend the language out and to have let expressions. In fact, we're going to need let expressions because we need places for more complex expressions. So we define this language or one which extends or not. It adds a new terminal of a variable. Okay, and now expressions can take in. Well, an expression can be a variable itself, or it can be a let expression too. that's the R1 language. It's just like the R not language, except it has let expressions. And then we can define this new pass called remove complex. So the code for this is sort of complicated, but it's going to look for an entry point called program, and it's going to pick apart its different programs, forms different pieces. So there's an info section, and then there's the expert. I'm going to be interested in the expert. So these are the different clauses that an expression can take. There's an addition, there's a subtraction, and then there's just a constant value. So this pass is actually kind of complicated. There's another little helper function right here called simplify store. Okay, and you can define a little helper function right here in the definition section of a pass. Okay. This is a well-known pass called simplify that uses the method of work lists. So we're going to have, let's see here. I'm going to use 3 work lists. Okay. We're going to define a loop. Well, I guess I'll say one more thing about this simplify. The way it works, just sort of looking into it, is we take a list of expressions in a builder, basically like a continuation, and produce a simplified expression in a let statement. Okay. So you start off with 3 lists. This T store is a list of temporaries. This TE store is a list of expressions. And this RE store is a list of arguments. Okay. So, and this E store is just the list of the expressions, the initial expressions. So, you know, when we've reached the base case, we know that we're done and we can build a let from those different work lists. This is a great feature of Nanopass, is that we can match on the expression right here. Okay, we can match on it in the or not language. In this case, it's pretty simple. Okay, so if this is a constant value, then we just add it to the list of expressions. Don't need to do anything special about it. But in the general case, you know, we want to make a new temp, make a new temporary. We want to add that to our temporaries list. And then we want to add the expression onto the, what is that? The expressions list. And then we want to add the temporary onto the arguments list, because now it's now simplified. Okay, and then once we build all those lists, we can pretty simply construct the let expression right here. Okay, so let me show you guys what the output of that language is going to look like. I'm going to pass this to parse. I'll pass this to complex. There you say it worked. It produced some sort of again, it's an opaque value. You can't really tell what that is. But you know, I said earlier that there's a way of defining a parser automatically. And if you do define a parser automatically, it also defines an unparser. So we can look at the output. Let me show you guys how to inspect the output. I'm going to call this parse or1. And that just takes as an argument the language. Okay, and I just sent that to my REPL. Everything looks good. Let's see, do we have unparse? Okay, great, we have unparse. Let's take that and try to unparse it and look at what that is as a scheme value, as a Lisp value. Okay. It didn't do anything. And it didn't do anything because there's nothing complicated about a constant integer. Let's look at maybe one example from earlier. Okay, and it works just fine. You can see it removed the complex expressions of the argument in the addition, in the first addition. Move that out into a let statement. This is really useful for debugging. Okay, so there's a lot more code here. Okay, the next pass turns it into a completely different language, the C0 language. And that's all I wanted to talk about today. It's just the very basics.
You should tell people that they should buy this book.
Oh, Essentials of Compilation.
I mean, you're referencing the example. You mentioned the book.
That's
This
it.
is it.
That's great. Yeah, that's a great point. I should have.
It's on Amazon.
You mentioned it on the screen.
Yeah,
A bunch of times.
It's literally right there.
Yeah.
Is it like a summary of Dragon?
It's a new book on
Essentials of
compilers.
Compilation is
Yeah.
great.
Yeah.
Really good.
And it just came out, right? It was available on GitHub for a while, but now
It's
it's printed.
basically the latest about how they teach compilers.
So it's like a modern.
It's very scheme or rather racket centric and very much the Indiana school. But if you've been reading all the papers that Dipig and company produced over the years, they're carrying on. This is the latest.
That's a great book. And if you go onto my GitHub, I have an older version of the book that's been compiled to HTML that you can just view on your website. So if you go to, I have a fork of the Essentials of Compilation starter code, and there's a really great resources for getting started with that book.
Yeah, there actually is a version of the book even off GitHub. It seems like at some point they just stopped kind of maintaining it there, polished it up pretty, and put it out in MIT Press.
I was actually following along with the class one of the last times before they published the book, and doing copy editing for him in that GitHub repo. I didn't actually finish the whole thing. Yeah, it seemed like a very well done class.
Yeah, so that's it, guys. That's the basics.
So basically, the idea is you use that to define phases of a compiler
Yeah.
that are each very well defined, and it's source to source to source to source to source until you get to.
It separates the act of compiling into a lot of different languages.
So we thanks to Stephen, and there was applause, but I had the microphone off. And I'm wondering if there are any questions. I don't think there are any questions online, so I think we'll end and go to the snacking and chatting phase, which only those of us in person can enjoy. So thanks, everybody. Really appreciate it.
Unfair.
Well, thank you, Jay.